Recording. Okay. Okay. So what you're going to do today first is quiz 0, which was like practice submission. Now, students have been doing this for the last year and a half, right? You've been scanning and uploading your assignments all through the pandemic year. And what I'm implementing this time is we'll do the quizzes in person in class, and then you'll scan and upload it to Canvas. Now, it's a very easy thing, very simple thing, but there's always issues that come up. Specifically because every course is a new website. If there are glitches in the system, or if there are glitches with that specific course website, then we want to catch it before something else happens. So what I'm going to do is I'm going to pass out these blank equation sheets. Now students can keep these, one for each student, and then you'll be using it for the quizzes going forward. All right. I'll talk more about the equation sheets and I'll post it. Well, actually not talk, but I'll post the details on Canvas. But what you're going to do for today, for right now, is the first 5 minutes until 9, let's say until 9, not 9, sorry, 10, 15, 10, 16. You would scan both sides, page 1 and page 2, create a PDF and upload it to Canvas. The upload link is quiz 0. All right. Actually, let's right there. Okay, so the upload link is on quiz 0. Online students, whoever's attending online, you take any random piece of paper, standard letter size, of course. You can have any assignment from your past classes. Scan at least 2 pages. Okay, scan at least 2 pages. Create one single PDF file and upload it to Canvas. Okay. As of now, I do not have any plans of allowing students to take quizzes online. So you can attend classes in person, but every Monday you would come to class to take the quiz, okay, in person. The only exception would be if there's a medical reason with a valid medical note. Okay, it's a little bit hard for me to proctor in person as well as online at the same time. So attending class in person or online is an option, but taking the quiz is not. All right, so online students, again, go ahead and scan any piece of paper as long as it's standard letter size. It could be blank paper, just write down your name on it, page 1 and page 2, and scan as single PDF file. Now, typically the way it would work in class is we would take the quiz. You'll have about 15 minutes, 20 minutes, 25 minutes, depending on the day and the quiz material itself. And then once I say time is up, you would stop working on it, and then you'll have 5 minutes to scan and upload it. And since we've been doing this in person, if there are any issues, I will know about it immediately. All right, let's check. Let's check and see. All right, assignments. So this is where you're submitting it. Quiz 0, student submission practice. That is where you're submitting this assignment or uploading this assignment. Okay. All right, the floor is open for questions. If anyone has any questions about today, about any of the material we have covered in the past, anything else? I assume at this point everyone has signed up. Yes. No. This is just an equation sheet. So yeah, no. Quizzes just depends. Typically, it's just like one problem. Depending on the material or the topic, it could be more. Yeah, so before every quiz, I will post an announcement and an email, like the topic, date, the time, and the material that needs, the prep material that students need to use. Yeah, everything will be there. Yeah. So From the system, I see pretty much every student, most students have signed up. I think there was a discrepancy between the course roster and the Canvas roster, so there are still some students who need to sign up for mastering. If you have not done so, please go ahead and do so at your earliest convenience. Homework 1 was due tonight. I think I may postpone it to tomorrow because there are a couple of topics in there that are not yet covered. So I would either cover them in class today, or I might post a video about it. And so depending on how and when we cover the material, I'll always move the homework dates around. Okay, I'll move the homework dates around. All right, we're up to 50, 10, 16, 10, 17. Online students, any issues?
No issues.
Okay, great. Is everyone here done? Anyone still scanning? All right, well, let's move forward with our talk for today. Okay, we stopped right here where we talked about sources, dependent sources, and independent sources. And again, as a refresher, independent sources are the ones that do not depend on any external factors to supply some energy. If it's a voltage source, it's going to supply a voltage irrespective of what it's connected at its output terminals. Current source does the exact same thing. It supplies a fixed amount of current. Doesn't matter what you connect at its output terminals. A dependent source, however, depends on something else. We will not do any problems or any problem solving using dependent sources, but it's just something that students should be familiar with, right? Okay, so Thor is here to help us. Well, not really. It's just a meme that I really like. It's been popular. I don't have any story about it, but I always like to include it. We already looked at, well, what a conductor is, right? It's a simple straight wire or a cable that conducts electricity from one point to another point. And then the three components that we would use, well, not use, we'll study in this class is a resistor, capacitor, and inductor. Like resistors basically are chapters 1 and 2. Well, actually, mostly chapter 2, resistive circuit analysis. And then chapter 3 is capacitors and inductors. Chapter 4 is transient analysis of resistors, capacitors, and inductors. Okay. So chapter 2 is resistive analysis. Chapter 3 is inductors and capacitors. And then chapter 4 is transients. And then transformers are basically based on mutual inductance. And so it's based on inductors. So we'll look at transformers a little bit. And then transistor is not part of 201. It falls under electronics. It is EE321. So if you take the follow-on course, which follows directly after 201, that's where you learn about semiconductor electronics. Okay, 7. All right, so as engineers in your own field, you would have worked with a lot of different problems analysis where you would encounter values ranging from very, very small to very, very large, right? So unit prefixes are a way of actually expressing very small or very large values in a very succinct manner, right? And as engineers, you are probably familiar with a lot of these. Like you'd start learning about these in like high school, and then you would have used it in many of the previous classes, specifically the ones in the middle of the board right here. This is just something I always like to bring up. I don't expect students to memorize any of these unit prefixes. Even I don't know the ones like at the bottom and the top of the table, right? But some of the most common ones that we encounter in everyday life are right here, right? You work with like kilo, mega, giga, tera. We work with like terabytes of data or terahertz of frequencies, gigahertz of frequencies. On the other side, we have milli, micro. What? We have milli, micro, nano. You know, nowadays they talk about micro technology, nanotechnology a lot. Those are all very, very small ranges. The way it's applicable to our course is like this, because we're working with very wide range of values. So as an example, voltages, let's begin with voltages. Voltages will typically be in tens of volts. Sometimes you might see kilovolts. Current typically is in milliamps or even microamps. Resistor values range from tens of ohms to kilo ohms and mega ohms. Capacitors are very, very tiny, very, very small in value. And so they are typically in microfarads, the micro range. Inductors are typically in the millihenry range. Okay. So now, when you are writing out an answer, let's say you have an answer of like 10,000. I'm sorry, 1,000. You could write out 1,000. You could write out 10 raised to 3, or you could write out 1K. All of these are acceptable. So what I'm trying to say is the answer is 1,000. You could write in any form you want. You can use a unit prefix. You can use an exponent. You can write out the value directly. All of the answers, I mean, all of the representations will get you full credit. Okay. As long as your numerical value is correct, you will get the full credit. Okay. So you can use unit prefixes or not. It's up to you. But again, as engineers in the scientific field, this is something that is very, very common, right? In everyday life, if you think about it, the electrical signals that we use in everyday life, you've already used it. Like cell phone signals, they run in the megahertz range. Wireless routers, your cordless phones, microwaves, they all run at 2.4 gigahertz frequency. Wireless routers now have dual bands, so it's 2.4 and 5 gigahertz dual band frequencies, right? That's where we use it. Hard drive storages are now in terabytes. Frequencies, clock frequencies for processors are in the gigahertz range. AM radio stations, FM radio stations, they are broadcast at kilohertz, so kilo and mega. If you've ever driven down the side of the highway, it says tune into 6:30 a.m. That 630 is the station number. And it has significance in that it is the broadcasting frequency of that particular radio station. So it's broadcasting at 630 kilohertz frequency. FM radio stations, 101.7 FM is 101 megahertz transmitting frequency. So again, it's megahertz range. The other one is kilohertz range. Terrestrial and satellite broadcast goes into like gigahertz and terahertz range. Okay, so we use those numbers in everyday life. Unit prefixes in everyday life, not just as engineers, but even in general population. One example I always like to I find fascinating is people throw around like millions and billions and trillions of dollars as if it's nothing, right? We talk about millionaires and billionaires. So when we talk in terms of money, I mean, we realize it's large amount of money, but just to give you an idea of how big the difference is, I like to use time as the currency. So 1 million seconds, 1 mega, 10 raised to 6. How much do you think is 1 million seconds worth in days, weeks, months, years? Any wild guesses from anyone? Online, in person? Anyone? Wild guess. It's not quite 2 years. It's 11 days. 11 days. At least she took a guess. No one else is taking a guess. All right, so let's go to 1 billion seconds. is 31 years. That's the difference between a millionaire and a billionaire. So when you replace money with time, I can illustrate how big of a difference one unit prefix would make. It's 11 days versus 31 years, right? You spend, even if you spend like, I don't know, $100,000 every day, I don't think you could spend $1 billion in your lifetime. But that's, that's the vast difference. There was a very interesting movie that came up. Why did it stop? Why did this stop? Okay. Online students, can you still see the slide?
Yeah.
Okay, I think it stopped for a little bit over there. Let's make this bigger. All right, so there was a movie that came out that I particularly like and enjoy watching, like every few months. It was called In Time. Justin Timberlake and Amanda Seyfried. Anyone seen that movie? That movie is all about using time as the currency. So it was not like a big hit, but it's very popular in some circles. And basically, the currency, as I said, it's some futuristic dystopian world where the currency is time. People just have a few days to live unless they earn more. They work and they earn more time. And of course, there are people in that world. There are people who have like months and years and hundreds of years and thousands of years. So again, that's a movie that I really like, and if you have the time and have access to it, definitely it's worth checking it out. Anyway, coming back from the tangent, unit prefixes. I don't expect students to memorize the entire table, but there are some values in the middle of the table that every engineer should be familiar with, right? We encounter it in everyday lives and also in your own engineering fields. All right, fluid flow analogy between electrical and mechanical. So we talked about a conductor, right? Any material that allows the conduction or passage of electrons is a conductor. Now, conductor allows the flow of current, right? Allows the flow of current. So if I was to use a mechanical analogy, I would say that this electrical conductor is analogous to a pipe, and it is allowing the flow of fluid, right? It's allowing the flow of fluid. In electrical engineering, we will use the concept of a switch, like an electrical switch, which is analogous to a mechanical valve. An electrical switch is displayed by this symbol, or is noted by the symbol. It's kind of like a flapper. This would be a wire or a conductor, and there is a switch right here that is connecting both ends of that conductor, right? If I was to draw a mechanical valve, again, this is a very rudimentary drawing. So I would have a pipe, and I would have a mechanical valve in there, simple flap valve, right? Obviously, again, as I said, it's very rudimentary drawing. But the electrical switch is analogous to a mechanical valve. However, the terms that we use to refer to both of them are exactly the opposite, right? They're exactly the opposite. Well, what can you say about the position of this valve? Is it open or closed? Any fluid passing through the pipe? No, right? It's closed. So this valve can be said as closed and no fluid flow. However, in the same position, the electrical switch is said to be open. Open switch, no current flow. Current needs a pathway to flow through. It's like a vehicle going on a road. If there's a break in the road, you cannot drive your vehicle there, right? There's a blockage or something. So similarly, current needs a pathway to flow through. If there's a break in the pathway, current cannot flow through. So if a switch is open, then no current can flow through. So the term is exactly the opposite of a mechanical valve. Okay. And then the exact opposite happens when it's closed. A closed switch is referred like this, meaning there is a pathway for the current to flow through. And so a closed switch allows the conduction of electrons or electricity. So closed switch is exactly the opposite of a closed valve. Make sense to everyone? Let's take 5 seconds. Let me know if anyone has any questions. All right. Okay. So when we first begin circuit analysis, we assign values arbitrarily or completely randomly. Okay. When we begin, we have no idea about current flow. We have no idea about voltage polarity. Now, current, of course, is defined as the rate of flow of charge, right? Current is defined as the rate of flow of charge. Current is represented by the letter I and has units named after ampere, or A for short. Okay. And current always has a direction. So it's always flowing from point A to point B or point C to point D, and it always needs a pathway to flow through. I is defined as the rate of flow of charge. Now, all of this may be familiar to students from your prereq physics classes, but you're still required to actually cover the material. We will use these techniques later on in this chapter and the next chapter, and so we do need to do a refresher. Q, of course, is charge. And then voltage is the difference in electric potential. So electric potential difference, right? Electric potential difference. Unit for voltage, and the name itself also comes from, anyone know? Named after volta. So it's volts. V for short. Now, current, as I said, is the rate of flow of charge. It means it's flowing through a circuit. So when it's flowing, we indicate the direction by using an arrow. Voltage is the difference in electric potential between any 2 points, right? Between any 2 points, meaning it is always measured with reference with 1 point, right? The word difference already indicates you're measuring with reference to a particular point. More often than not, that reference point is ground, 0 volts. Okay, more often than not, the reference point is ground, right? 0 volts. But it's always the difference in electric potential between any 2 points. So current is always represented with an arrow. Voltage, because it's the difference, has a polarity. We would say one end is, or one point is higher than the other. So we would say plus and minus. The higher point is indicated with the plus sign, lower point with a minus sign. Okay. So because it's a difference in electric potential, we would say the higher point has a plus sign and the lower point has a minus sign. And if both points are at the exact same potential, what is the voltage? 0 volts, right? 0 volts. So when we first begin circuit analysis, again, our purpose of circuit analysis is to determine the values of the unknown currents and unknown voltages, right? We don't know what the values are. We don't know the direction of the current. We don't know the polarity of the voltage. So we start assigning signs randomly or arbitrarily, as I say, right? When I say values, I'm talking about like signs and notations. So here, let's say in this example, we know the values of A, B, C, D, and E, the component values, right? We know the values of these components, and we know the values of 1, 2, 3, 4, 5. If there is a source in the circuit, we may know perhaps the voltage being supplied by the source, or we may also know the current that's being supplied by the source, right? But those are the only things that we know. Everything else we need to determine. So we start assigning values, we start assigning current directions, we start assigning voltage polarities arbitrarily, completely randomly. We make certain assumptions. So we make certain assumptions for direction and polarity. Okay, but those assumptions are based on certain logic. Well, logic and laws, of course. Okay, so we make random assumptions about the circuit, but those assumptions are based on logic. So here, I1 is going up, I2 is going down, I3 is going down, right? So those are assumptions on my part. I just assume that I1 is going up, I2 is going down, I3 is going down. And the same thing with these voltage polarities. Okay, those are all assumptions. Now, there is no right or wrong value for assumption. Even if you choose a direction or polarity that is going against all logic, that it goes against all laws, your answer would still be correct. And the only thing is that your answer would have a negative sign. Okay, so even if it's opposite, the example would be this is negative. Let's use I3 as an example. If my value for I3 turns out to be minus 5 amps, what does that minus indicate? It's going the other way. Exactly. That's all it means. It does not mean anything else. So the point or the takeaway point from here is no matter what you choose, no matter what you assume at the beginning of the problem, as long as you're consistent within the problem itself, your answer will always turn out to be correct. Okay. So if you choose I3 as going down, your answer comes out to minus 5 amps. If in fact I3 is actually going up, your answer would be plus 5 amps. You would still get full credit. So I will take a look at your value. I will also take a look at the arrow direction or the polarity that you've indicated on the circuit diagram, put those two together, and then assess your work. right? Now, if the arrow is going up and you get minus 5 amps, then that is incorrect. Does that make sense to everyone? Right? So assign values randomly, doesn't matter. I mean, we take logic and laws into account, but even if you go against logic and you choose something else, it does not really matter, as long as you're consistent. When I say consistent, meaning halfway through the problem, you cannot change the direction of the current. Like if you're applying KCL or KVL at this point and you choose I3 as going down, now if you apply KCL at that point, you cannot change the direction of I3. If you choose a direction or polarity of I3 at the beginning, then you stick with that assumption until the end of your analysis. So you have to stay consistent for the entire problem. You cannot change your assumptions midway through your solution, right? So as long as you're consistent, you'll always end up with the right answer. All right, take 5 seconds. Let me know if anyone has any questions. Any questions from anyone? Online students, are we good? We good?
All good.
All right, thank you. Feeling a bit chilled now. Okay, so as I was saying, current moves from one point to another point. Voltage is always measured between 2 points. And so we always use a 2 subscript notation, right? We always use a 2 subscript notation. Actually, let me. I'll come back to voltage polarity and direction later on. I want to get done with KCL and KVL. Then I'll come back there. This is a meme that's very popular to describe Ohm's law. It succinctly summarizes what actually Ohm's law is and the relationship between the 3 quantities, right? So George Ohm was a physicist, scientist, researcher who did a lot of research in resistances, its properties, and the relationship between the resistance, current, and voltage, right? George Ohm. And the unit for resistance came to be known or came to be named after him. So R is Ohm and symbolized by the Greek letter omega. Okay, Greek letter omega. Now, this is the uppercase omega. There's a lowercase omega that looks like a W, and we look at that in chapter 5. Okay, again. And then, of course, V equals IR. That is Ohm's law. Simply stated, when current flows through a resistance, it causes a voltage drop. The voltage drop is directly proportional to the product of the current and the resistance itself, right? So V equals IR. It's the most fundamental of all physics laws that applies to electrical engineering. You can solve pretty much any circuit. Well, we cannot solve any circuit without Ohm's law. Let's put it that way. There are other methods, other techniques, other analysis techniques that you will learn, but this is always the starting point. Like Ohm's law, you can apply to any component. It will always hold true. We'll come back to power later. Let's go to KCL and KVL. Okay. How would you say this name? Kirchhoff, Kirchhoff. So I'm from India. The way we pronounce this name over there is Kirchhoff. And that's how I learned it. So if you ever hear me say Kirchhoff, that's who I am referring to. When I first came to the US as a grad student many years ago, I was in a meeting and somebody was talking about Kirchhoff. And I was like, I'd better keep my mouth shut because I have no idea what they're talking about. And then a few days later, that's when I realized that's who they were referring to. There was a German physicist, a researcher, who came up with a few laws regarding current and voltages in a circuit. And they were based on the law of conservation of energy, right? The actual German pronunciation for this name is Kirchhoff. Now, none of us were alive during his time, so we don't know if that's how his name was pronounced. But in modern day Germany, that's how the name is pronounced, Kirchhoff. Anyway, so based on his work, We have Kirchhoff's current law and Kirchhoff's voltage law, KCL and KVL. Basically, it states when you sum up all the currents, whether around a node or electrical junction, they should all equal 0. If you sum up the voltages around any electrical loop, they should also equal 0. Law of conservation of energy, everything that a source is supplying in a circuit has to equal the energy that is being received in that circuit. So you have a circuit that comprises of sources and loads. All of the energy from all the sources put together has to equal all of the energy that is being received by all of the loads in the circuit. All right. So if we take an electrical junction as an example, I would think of it as, I always like to use a vehicular analogy, like a traffic junction, right? If you have a traffic junction, all of the vehicles that are entering that junction have to leave or exit the junction, right? Otherwise, you'd have Die Hard 4. You remember that scene, right? All systems go. It's physically impossible, right? So, well, actually here. So let's draw current directions. What happened here? There's something weird about this computer. Seriously, it's drunk. It's happening yesterday also. Well, let's hope it works now. Okay, online students, can you still see the slide?
Yep.
Okay, thank you. So let's say you have 4 currents, IA, IB, IC, and ID, right? So the way I write out my KCL equation is like this. Now, before I do that, if you have a particular method that you're comfortable with for writing out KCL and KVL equations, feel free to continue doing so, right? I'm not evaluating you on how you're going to apply it. As long as the equation is correct and your answers are correct, it's absolutely fine. So a lot of the professors' methods students like to use is basically equate everything to 0, right? Sum of all currents in a junction or through a junction has to equal 0. But then you have to worry about a plus and a minus sign. So what I do is I simply have my equation and I sum up all currents entering the junction all currents entering the junction and all currents leaving the junction are on the right side. And I have my equation. That's it, as easy as that. Again, if you have a particular method where you are just summing it up as equal to 0, that is absolutely fine. For me, what I do is I take the equation, I put all the currents that are entering a junction on the left-hand side, all the currents that are leaving the junction on the right-hand side, and I get my expression, my equation. So in this particular case, I would have IA entering the junction, and that would equal IB plus IC plus ID, right? IA plus IC plus ID. So with this example, yeah, so with this example, we would have IA is entering, and then IB, IC, and ID are all leaving. And so we would simply just write it out like, all the currents entering are on the left hand side, so it's only IA that's entering, and then everything else is leaving. So we get IB plus IC plus ID. Yes. Yes. Sorry. Yeah. I'm just referring to this one right now. Should have mentioned that. Yes. So let's look at the example that's in the slide now. This one. Okay. Let's look at, well, since the question is being asked right here, IB, let's deal with IB, right? So if you look at IB, IB is the current that's passing through element B. So I can apply KCL either at the top or I can apply KCL at the bottom. Let's call this node 1. Call this node 2. So at node 1, what do I have? And now I'm solving this problem, right? So at junction 1, if I write my KCL, I have IA entering the junction. Then I have IC entering the junction. And IB is leaving the junction. And so that goes on the right-hand side of the equation. And so IB is equal to IA plus IC. Does everyone see that? Make sense, right? Easy enough. You have IA entering the junction. You have IC is entering the junction, and then IB is leaving. And so you would get IA plus IC, of course, is going to give me 6 minus 2. And so therefore, IB is 4 amps. Make sense? Any questions from anyone? And then you have ID up here, but ID is actually going the opposite of IC. So you would say IC is equal to minus ID. And you just flip the sign. So if I was to apply, let's say, well, let's call this 3. So node 3, I would write, nothing is entering the junction, which is not physically possible, obviously. But mathematically speaking, I can still write it out. So at node 3, I have only 2 currents, IC and ID, and both of them are leaving. So I would have 0 equals IC plus ID. Right? Make sense? And then ID is equal to minus IC. And IC is given as minus 2 amps. And so this simply becomes ID is equal to 2 amps. Does that make sense to everyone? Any questions? Let's take 10 seconds. Let me know if you have any questions. Again, this is something that students have done in the past, just a refresher. And there's a homework regarding KCL and KVL. It's again, just for, as a refresher purposes, just make sure that students are up to speed. And the assumption is that students are already familiar with these laws. Yes. No, it is realistic. It is just, yeah, it's just the illustration is against logic or against laws, but it's still realistic. Yes. Yeah. Yeah. That is, again, the example is specifically to show that doesn't matter what direction we choose, right? So let's say we were starting to solve this problem and we choose something like this. So even if the assumption is going against logic, it's going against all laws, your mathematical solution will still end up being correct. Yeah. All right, few minutes left. Let's go to KVL. Oh, this I'm going to assign as student practice. So practice this outside of class. Here in A, I can see I have 2 currents entering and 1 current leaving. Here I have 1, 2, 3 currents entering and 1 leaving. And here in C, I have 4 currents entering and 0 leaving. Okay. So again, assigning a student practice outside of class. KVL. KVL again is basically based on law of conservation of energy. You have an electrical loop. If you sum up all of the voltages around that loop, they will always sum up to 0. Okay, so we have loop 1, loop 2, and loop 3 here. The way you can determine a loop is basically pick a starting point. I always pick the bottom left corner of a circuit. So if I choose this corner right there, right below A, and I go around my pathway and I come back to the same starting point, that is one electrical loop. Okay, that is one electrical loop. I can start at the same point and take another pathway and come back to that same starting point. That is another loop. Again, any pathway that allows me to come back to my starting point is an electrical loop. And the beauty of KVL is it works with any loops. Doesn't really matter what kind of circuit you have, complex circuit with hundreds of components, KVL always holds true. I mean, there's a physical basis and a physical explanation for how and why it works, but it's just beautiful to me that it just works every single time. You know, it's just based on law of conservation of energy, and it just works. Loop 2, if I start at the junction that is below C, and I go around C, D, and E, that is another loop. So you have 3 loops in the circuit, right? Any electrical pathway that allows you to come back to that same starting point is an electrical loop. It's a closed pathway. So the way I apply KVL is I sum everything up to 0. So what I would do is, and again, every student has their own way or own method that they prefer. So you can write it up any way you want. What I'm going to do is I always start at the bottom left corner of my loop. So I'm taking loop 1 and I add up the voltages in a clockwise direction. So I have 3 voltages in loop 1. So starting at the bottom left corner, I have VA, I have VB, and I have VC, and they should all sum up to 0, right? They should all sum up to 0. VA, VB, and VC should all sum up to 0. Now, the way I would add or subtract the voltages is I would go around adding the voltages in a clockwise manner, and I would enter the sign as the first polarity that I encounter for that particular voltage. So if I start summing up the voltages in a clockwise manner, VA is minus first. Does that make sense? I'm going in a clockwise manner. So VA is minus, VB is plus, VC is plus. So minus VA plus VB plus VC equals 0. That is my mathematical expression. Again, if you have a particular method you want to use, that is absolutely fine. And if you choose to add it up from a different point, you would still get the exact same equation. If I start at the same point and I go counterclockwise, if I start at the same point and I go counterclockwise, I now have VC, VB, and VA. And this time, VC is minus, VB is minus, and VA is plus. So I'm starting at this corner, bottom left corner, and going in a counterclockwise direction. So I got minus, minus, and plus. Exact same equation, no difference. Same mathematical expression. So again, doesn't matter what we choose, your equation will always remain the same. All right, any questions? Okay, so we'll have a quiz on Monday. I'll post all the details on Canvas. Again, students need to be here in person. I will also post details about the equation sheet. Let's see. There's KCL and KVL homework that is available on Mastering. So the due dates are not until next week, but you can use those to practice and get up to speed. Most likely, the topics that I will have on Monday will be regarding KCL, KVL, and some of the basic stuff that we have covered so far. If there's something else, again, I will post it on Canvas and make sure everybody has the information. All right, have a good weekend, and I will see you all on Monday. I'll be in my office until 4 o'clock today, and then available all weekend via Zoom. So if you need to see me office hours, I'll be available all weekend. All right, I will see you all on Monday.
Thank you.
Yes, yes.
One of the
Let me stop the recording. So, yeah, go ahead. I'm listening.
so the